Hello student, let's start with our new topic which is little bit differ from our previous cases. In previous cases we have understand about the member consists of a single member which is connected with gusset plate and loaded with some force. In that case, we have studied about the design tension capacity of the member. Means that section is a type of analysis of the tension capacity. In that case, we have studied about the finding out the different capacity, tension capacity of the member. In that case, first one is strength for the cross section, second one is strength for the rupture of net area, and third one is block shear if it is there. From that three, whichever is smaller, that capacity is considered as the design tension capacity of the member. So, up to here we have taken only a member which is single. Now we are talking about the built up section, and you know what is built up section. In our theory portion we have clearly understand the built up section. Still I am going to repeat that whenever our section is made up from the different members, that is known as the built up section. Like अगर हम दो एंगल को कनेक्ट करके एक मेंबर बनाते हैं, दैट इज कॉल्ड बिल्ट अप सेक्शन. तीन प्लेट लेके एक आई सेक्शन बनाते हैं, दो प्लेट लेके एक एंगल सेक्शन बनाते हैं, दैट all are known as a built up section. So now we are going to finding out the tensile strength of the built up section, right? So now you have clear idea about the built up section. Let's start with next case. Here I have taken one single case for the understanding of the whole idea about the built up section and its tension capacity. A tension member consists of two angles 90 by 90 by 8 mm bolted to 10 mm thick gusset plate on either side of gusset plate using single row of bolts and tack bolted. Determine the tensile capacity of the member and number of bolt required to develop full capacity of member. Now here two things are new for us. First one is tack bolted. What it means? Whenever we are going to make a built up section, so it is connected on either side of the gusset plate, right? So we have thickness of that gusset plate is 10 mm. Now the member is connected over this end and connected over the next end. In that case there is a gap between two members of 10 mm. So that gap is generating our section as a different section. So we have to consider as a single member, then we must have to tack bolted at 0.5 meter distance or else at 1 meter distance, whatever we have decided. That is called tack bolted. And In previous cases we have understand that the design tension capacity, but the bolts and number of bolts and position of that bolts are given. In this case we have to finding out the number of bolts. So the methodology is same, but calculation are little bit different as compared to our previous cases. Now here what they have given, two angles connected on either side of gusset plate. This is our gusset plate and two members, it is angle section, and that angle section is connected either side of this gusset plate with 20 mm diameter bolt. Here I have assumed this diameter of bolt because they haven't given the clear idea about that bolts. And the side view of this section is, this is our gusset plate and this is our angle section. This is the outer outstanding leg is indicated over here, and number of bolts right now we don't have, so we have just assumed that 5 or 6 bolt is there. Means here the depth of this section is 90 mm, this is also 90 mm and thickness is 8 mm. So we know that our bolt is provided at the gauge distance which is given in steel table as well as in SP6. We have to take 60% from the outstanding leg. So it is 60% of 90, that is 54, but here we have taken the 50 mm as a round figure. So it is 50 mm and it is 40 mm from the top. Now our step, that is first we have to finding out the tension capacity for the gross section. Means we have to calculate the full strength of this member. For that we have to calculate the area of this built up section. So let's start. First, design strength due to yielding of gross section. Now for that we have diameter of bolt, that is 20 mm, we have assumed over here. Overall diameter is 20 plus 2, that is 22, which is given on page number 73. As we know, Fy is 250. For any section that we can choose from this steel table, that Fy is always 250 and Fu is always 410 megapascal. So we can take directly. Now the gross area Ag is 2 times of 1379. It is 1379 is a area of single angle that is comes from the steel table, and here we have taken 2 angles, so multiply it with 2 and we will get 2758 mm square as a gross area. Now we have equation of the design tensile strength for the gross section, that is TDG is equal to Ag into Fy upon gamma m0. We have this Ag, Fy we have, and gamma m0 we will take it from page number 30 in steel table, and this equation is given on page number 32 in ISO 800/2007. So the TDG is equal to 2758 multiplied by 250 divided by 1.10. It is gamma given page number 30. So we will get TDG is equal to 626.82 kilonewton over here. Now the second thing, that is design strength due to rupture of net section, that we have to calculate it from the page number 33. And whenever we have this kind of built up section, then we must have to take equation of with alpha. Now TDN is equal to alpha into An into Fu upon gamma m1. Now the difficult task, that is finding out the An, and how we will get that An? An is equal to 90 minus half thickness minus diameter of hole into thickness of angle plus the outstanding leg, that is 90 minus half of thickness multiplied by 8, and this whole is multiplied by 2 because we have 2 angle over there. And whenever we are going to take built up section, then alpha is there, and this alpha is come from the bolts. So in that case we must have to consider that our number of bolts are more than 4 bolts, so it is 0.8 over here. Now we have net area, that is 2400 mm square. Clear? Now we have alpha, we have net area, Fu already we have 410 megapascal, and gamma M1 which is given on the page number 30, IS 800 2007. So it is 1.25. So we are going to put that value in our equation and we will get TDN, that is 629.76 kilonewton. Now the third thing, that is block shear failure, and for that we have to first finding out the number of bolts. So for the finding out number of bolt, we have to take smaller value of this TDG and TDN, and we will get 626.82 as a TD, means this much force is acting on our section. Now for the designing of bolt, we have to finding out first end distance, that is 1.7 into diameter of hole, and that is 37.4. So we are going to take over here 40 mm as a round figure. Now the next is finding out the pitch distance. Whenever we are going to calculate any bolted connection and any number of bolt, we have to find out first end distance and pitch distance. So here we have pitch distance, and that is 2.5 into D. These things already we have studied in our previous chapter, that is bolted connection. Now we are just repeating that bolted connection over here, and that is 50 mm as a pitch distance. So the section is built up, so double shear is generated. You know that what is single shear and what is double shear. So here the double shear is there. So the double shear capacity of the 20 mm diameter bolt, that is 2 into 45.3. So we will get 90.6 as a shear capacity for the double shear. Other capacity of the bolt, that is bearing capacity, that we have to calculate it, but whenever this kind of case, we are just taking the single shear capacity as our bolt value. Now here we are going to take bolt value as a 90.6 as a bolt value. We are not going to finding out the bearing capacity because the example is of tension member, and there is no need to calculation of this kind of bolted. Now we have the bolt value, that is 90.6 kilonewton. Now number of bolts required for that, that is 626.82 divided by 90.6, right? So we will get 6.91. So we have to take 7 number of 20 mm diameter bolts over here, and we will, whenever we are going to put this 7 bolt over here, so we will get this kind of section. Let's, here this is our gauge distance 50 and this is 40. Now the first, that is end distance, that is 40, and remaining all are pitch distance, and last one is again end distance. But whenever we are going to considering bolt failure due to block shear, at the time this much section must be fell due to block shear. So for that we have to take part of the failure part of this block, and that is this kind of. Here 40 mm, this is 340 mm, the full length of the cutoff plate, and this is our bolt from where our section is failed. Now from this we have to finding out AVG, AVN, ATG and ATN, and these things are clearly understood by us in our previous chapter, that is bolted connection. So AVG is equal to 2720 mm square, AVN is equal to 340 minus 6.5 of 22 diameter of bolt multiplied by 8, means the total length is 340 and this is one bolt 22, 2, 3, 4, 5, 6 and half of this means it is 6.5. So we will get 1576 mm square. Now ATG, it is a vertical failure due to tension of gross, that is 40 by 8, and ATN is from the bolt failure. So 40 minus 0.5 into 22 multiplied by 8, that is 232 mm square. Now this is our raw material for the equation of block shear, and that two equation is given on page number 33 in IS 800. The first equation, that is TDB1. So here TDB1 is equal to AVG into Fy upon root 3 into gamma m0 plus 0.9 ATN into Fu upon gamma m1. This equation is given on page number 33. Now the value that we have, so put that value in this equation, 2730 plus into 250 divided by root 3 and gamma m0, that already we have. Here 0.9 into ATN that we have calculated, Fu we have, and gamma m1 also we have. So we will get TDB1 is equal to 4,25,393 Newton, but here we are going to calculate all that things in kilonewton. So TDB1 is equal to 425.39 kilonewton. Now another equation for the block shear failure, that is 0.9 AVN Fu by root 3 into gamma m1 plus ATG into Fy upon gamma m0, that all this value we have. So whenever we are going to put these values that we have already calculated, and we will get TDB2 is equal to 341,330 Newton. So we will get TDB1 is equal to 341.33 kilonewton. So here we have these two capacity due to block shear failure. So we will consider smaller of these two as a block shear. So the TDB smaller of that two is 341. So whenever we are going to take the full value, that we have section, that is 2 sections, so multiply this value as a 2. So the TDB1 is equal to 682.86 kilonewton. But what is the TD? TD is the smaller of TDG, TDN and TDB. So the design tensile strength of the section, that is 626.82 kilonewton. So in this case, the change in the calculation, that we have to finding out the number of bolts is little bit different, and the built-up section, for that whenever we are going to calculate the multiplication of that by 2 as a 2 member in our built-up section. So dear student, whenever this kind of case we have the built-up section, then this kind of calculation must be done by us, and we will get the final design tension capacity of the member. Okay, thank you. Now in a next lecture we are going to discuss about the design of the member, design of the tension member, and we have the steps for the tension member. Whenever we are going to design the tension member, first we have to calculate the size of the member, because in analysis case we have the member that we have to connect it, and sometimes we have number of bolt is also there. But whenever we are going to design, first we have to finding out which section is required over here. So the design step is little bit different as compared to analysis. Clear? So in next lecture we are going to understand about the design of tension member. Okay, thank you very much.